Main idea of the system. Information passes through node, then it suffers change. If new version of information makes to grow utility function of the whole system, signal stays in that node during the next step, and again some mutations are done to it. We keep using current node until value of the utility function tends to decline. In case of lowering of the utility function, information string seeks another node. Now this search of a node is not so random like in the previous version. Now node exists in n dimension, so they have coordinates. So as data signal does. On Bain or at a given point, we can calculate a vector of probabilities, which in turn are calculated based on the inverse distance of nodes to the current location. From this array we sample the next node. As you see, the closest nodes are sampled more frequently. Question is how we should place them. Some semantic can be implemented, but whatever for now. Firstly, I tried a new engine on forecasting functions like this. Not bad result, I think. I used rather simple nodes, like multiplying by parameter, sign on the data, adding integer, but I checked also some fancy things, like linear regression or subdimension with its own nodes. Node can be everything. Then I tested it on the initial claims. Results are better than the ordinary neural network shows. Much better, by the way. Now I want to explore this voyage-style symbolic optimization on the classification task. What about famous Pokemon dataset? I explored two types of species, grass and electric. Great power of my method is unnecessary differentiability of the loss or utility function. So, how about simple accuracy for grass Pokemon or electric? And now we can use special nodes optimization. I sampled labels based on the usual sigmoid function used on logits. I had some issues. NumPy hardly affords big numbers, and I neglected normalization this time. So I had to try some strange thing. I constructed labels on basis of excess above average of logits. For example, if we generate 20 and the mean of logits is 10, model gives label 1. Of course, for test sampling, I used average on the trained data. Results are funny, but it works, and we need no gradients, even for classification task. For the trained data, our model gives around 60% accuracy and 57% for test 1. Runs with train accuracy higher than 70% give more than 60% for the test data. Some of runs are not good at all. System constructs a route between nodes, and the probabilistic character of the choice leads to very different paths. But we can analyze and memorize them. Nodes are not tailored for classification tasks, but something is happening. Model is interesting, but nodes themselves should be remade and tailored for classification tasks.